God willing, in this video, we will talk about ultrasound physics. Inshallah, in this chapter, we will talk about ultrasound physics. We hope to cover this ultrasound section in 2 lectures or possibly 3 lectures, inshallah. In this chapter, we will start with an introduction to ultrasound, and then we will discuss the ultrasound beam itself in more detail. After that, we will talk about the interactions between ultrasound and the body, as well as the types of interactions that may occur. Hopefully, this will provide a more detailed explanation of the ultrasound beam itself. All right, by God's will, as I mentioned to you, we will talk in this chapter about ultrasound. We will discuss the topic from the beginning. What are the characteristics of the ultrasound beam, the characteristic features of ultrasound, whether it is frequency, velocity, or wavelength, all the parameters related to ultrasound pulses or the ultrasound beam itself. Then we will look at how these ultrasound interactions occur and what types of interactions take place. Next, we will discuss how the ultrasound image is formed. After these interactions, what factors affect the image quality and how to determine the image quality or measurements or quantitative analysis regarding image quality. After that, we will talk about ultrasound artifacts and ultrasound safety, which are well known, as you all know, and most of you are, of course, working with ultrasound. Oh, what comes next is that we will also talk, God willing, about the imaging process. As you all know, we indeed use the probe itself in the imaging process. The idea is quite simple. I actually use the probe to generate pulses, which very much start to enter or interact with the tissues present. There are, of course, different types of interactions that occur, but initially I have the source of ultrasound, which is in fact the probe. This probe has a technique that we will discuss shortly, and it emits the ultrasound pulses. So now I have the source of ultrasound, number 1. The production process for the ultrasound pulse is taking place. This ultrasound pulse has specific characteristics, including a certain frequency and wavelength. The pulse is produced at a specific frequency, meaning, for example, I produce a certain number of pulses per second, or what is referred to as pulse rate frequency. Welcome to the stage of the countries. All of this distinguishes the type of pulse. Is this pulse considered a short pulse or a long pulse? We will discuss all of this. Well, after the pulses start to enter the tissues of the patient, they will indeed certainly experience or undergo certain effects. Different types of interactions can occur during transmissions. For example, in the part that is reflected or the part that returns, which I call an echo. Depending on the intensity of a certain signal, the probe starts to record or receive this signal again. You will find that you have a certain pulse, and then the probe will begin to reflect this second signal. This signal, when it comes with high intensity, I only take the signal that has high intensity, for example. and translate it into a specific color within the image. Ultrasound, or low intensity, I translate it to another color, which I call high intensity. For high hyperecho and low intensity, I have what is called anechoic, hypoechoic, and hyperecho, just as you all know. If the heights are high in this form, they are high in this form, or if their heights are very low, they are high in this form, or if they are high in this form, they are high in this form, or if 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 they are high in this form. The hyperecho and the anechoic appear in a way similar to a neoplasm, as shown here. All of this is based on the ultrasound physics. This is the reflected pulse, or the reflected intensity of the ultrasound pulses that the probe receives and records according to the intensity, which is the reflected intensity that starts to translate into my color. This, of course, is what happens when I have a transducer or a probe. The probe consists of a group of elements, as we will discuss later, where each element is responsible for producing the ultrasound pulses. These pulses, as we see, start to move in their line or path and begin to encounter a reflecting surface. This reflecting surface will start to reflect the intensity or a part of the ultrasonic waves. There is, of course, a part that undergoes transmission and a part that undergoes reflection. We will discuss later why reflection occurs in the first place. So, how does this reflection or low reflection occur? It depends on the signal returning to be received by my element or the crystal itself that is present in the transducer. It starts to give me the electrical signal, and this electrical signal is translated into an image. The whole idea is that I have an electrical pulse, and this electrical pulse stimulates my crystal to emit the ultrasound beam or the ultrasound pulse. This ultrasound pulse penetrates the patient's body. Part of it experiences attenuation, meaning a loss of energy, while another part undergoes transmittance and another part experiences reflection. This, of course, depends on many factors, as we will discuss later in the interactions. The part that was reflected starts to return. Once it returns, it is received, and then translated according to the second signal that was emitted. It begins to give it color on a grayscale related to or indicated by the intensity of the received signal. It starts to assign it its color, as we mentioned earlier, whether it is a hyperecho signal, hypoecho signal, or an echo signal. It can have those colors, as we said before, whether it is a hyperecho signal, hypoecho signal, or an echo signal. All right, this is the idea. In brief, the concept of ultrasound. I have a source, which is the ultrasound beam, and this beam has certain characteristics. It interacts with the body or the patient. Part of it gets reflected, part gets scattered, and part experiences attenuation. The reflected signal is then received by the probe, which translates it into an image. This is the main idea, or the basic concept of ultrasound. Now, when we talk about what ultrasound actually is, and consider the difference between ultrasound and X-ray, as we discussed in all the previous chapters about X-ray, electromagnetic radiation, gamma rays, X-ray production, and the X-ray tube, we noted that X-rays are electromagnetic waves that do not require a medium to travel through. As we were thinking, if I have a vacuum, the X-ray can travel in it. The ultrasound wave is considered non-ionizing, but there are some misconceptions that say ultrasound is non-ionizing. It is a type of mechanical energy, meaning that for it to propagate, a medium must be present for the sound waves to move through, unlike X-rays, which do not require a medium. Let's look at the shape of X-rays and sound waves. Here, X-rays are called transverse waves, while ultrasound waves are called longitudinal waves. What do you notice? You can see that in the transverse wave, the shape of the wave is like a sine wave as it moves in a direction. If you notice here, in a transverse wave, there are two things happening. The wave is going up and down. What is the direction of this movement? The direction of the electromagnetic waves themselves is vertical, perpendicular to the direction of wave propagation. The wave's propagation direction is from left to right, but the wave itself is considered vertical or perpendicular to the propagation from crest to crest. But when we talk about ultrasound waves, there is no such wave. Why? Because the direction of movement in ultrasound waves is considered parallel or in the same direction as the propagation. Here, for example, we have electromagnetic waves like X-rays and gamma rays. What are they? They consist of an electric field, which you will find here with a blue wave and a red wave. The blue wave represents the electric field that I am referring to as electromagnetic waves, meaning electric and magnetic waves. The electric field is perpendicular. If we assume that the black line represents the propagation direction, the blue wave is perpendicular to the propagation direction, and the red wave, which is the magnetic field, is also considered perpendicular, but takes another plane or shape. If we assume this is vertical, then this is horizontal in this way, but at the same time, it is as if it is entering the power point in this manner, so it is also perpendicular to the propagation direction. This is what happens in transverse waves, which are X-rays. Come and see its shape here. Here you find the electromagnetic field E and the blue B, which is the magnetic field. See? Both move perpendicular to the direction of wave propagation, which is the propagation direction. This is the electromagnetic field, but when we look at the ultrasound wave, you find that it operates differently. Its movement depends on the fact that it moves. For example, I want mechanical energy. This energy, is transferred to the particles in the medium. After that, the particles move, causing a transfer in a specific area where energy moves from one particle in a group to another group, resulting in areas of movement and areas without movement, like this view. Subscribe to the channel. The transfer of energy from these particles to other particles involves the movement of the particles themselves in the same direction as the wave propagation. The compressed part is the peak for me, or the compression, which is considered the high energy or the highest amplitude for me, where there is high pressure for the particles or the molecules present, and it has high energy. On the other hand, the part with rarefactions, which you see, is the part I refer to as rarefaction in Arabic. This is the bottom of the peak of my ultrasound beam, right? So it takes the shape of a sine wave. This is the direction of propagation. 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 After the energy is converted to millijoules, a medium is necessary. For me, sound waves need a medium to move through. The X-ray or gamma ray always travel at a constant velocity, which is the speed of light, meaning X-ray travels at the same speed as light, approximately 3.8 meters per second. This speed is constant regardless of whether we are talking about X-ray or gamma ray. It is a fixed speed that is not related to the type of medium. On the other hand, ultrasound waves are different. They are mechanical energy and their speed is mechanical. The speed of waves depends on the medium, meaning their speeds in water are different from their speeds in fat, different from their speeds in soft tissue, and different from their speeds in bone, and also different from their speeds in air. This is because it heavily depends on the particles present in the medium. As I mentioned earlier, when we talk about ultrasound waves, I said that the molecules are moving. So it depends on the distances between the particles. Are these distances close or far? because if the distances are close, the energy transfer process is easier. For example, if I have a particle next to another particle and the distances are very close, like when we talk about bone, this will help the energy transfer process or the transfer of ultrasound waves to be easier, unlike when we talk about air, where the interspaces or the distances between the particles are larger. The transition will be slower, right? Of course, we will discuss this part when we talk about the PIMP properties or the characteristics of the speed of the ultrasound wave. So we have now understood the spatial difference between X-ray and ultrasound wave. Humans can hear ultrasound waves, and there is also infrasound, which has a specific frequency below 20 hertz. When I say 20 or mention hertz, it means how many cycles per second. What does cycles per second mean? It means I am saying my wave looks like this, okay? I have a peak and then a bottom. This area where I perform the dashing process is considered a cycle. How many cycles per second do I have? When I say I have 20 hertz, it means 20 cycles per second, which means that the dashing cycle I am creating occurs 20 times per second. This is the meaning of hertz or cycles per second for me. As for the audible sound that I can hear, it ranges from 20 to 20,000 or 20 to 20,000 hertz. In 2020, Susan Hertz discussed ultrasound, mentioning ultrasound waves and their ranges. For me, in the diagnostic process I use, the frequency ranges from 2 to 12 hours up to 15 megahertz. Megahertz, of course, is 1 million cycles per second, which means 2 million cycles per second. This is a very high frequency that an average human cannot hear. We have a certain range of frequencies that we can hear. Even some sounds in nature are inaudible to us because they have frequencies outside the range that humans can perceive. Humans can hear certain frequencies. So this is the frequency I am working with, which is in diagnostic ultrasound, representing the number of cycles per second. Now, I was just talking about the probe. The probe, as you all know, has its applications, whether it is a convex probe, linear probe, or sector probe. We will also discuss in a lecture about the probes, their applications, and how their construction works internally. But let's talk about the basic idea of how ultrasound production occurs. The whole idea is in an experiment called the tuning fork. If you remember, we use something called the tuning fork. In the physics lab, they use it to create vibrations. When the tuning fork is struck, if we pay attention to ultrasound, I was talking about it being mechanical energy, right? So it is energy based on mechanics, dependent on movement. Movement is necessary to produce ultrasound waves. This movement is calculated at a certain frequency, at a specific speed, to generate those ultrasound waves, which are represented by the tuning fork. For me, the tuning fork, when I apply a certain force to it, starts to vibrate and produce sound. If I bring the tuning fork close to your ear, for example, you will hear a specific sound starting to reach you. The vibration and the sensation that occurred are thanks to the fact that I started to generate or emit the ultrasound waves that began to create the compression and rarefaction present in the air particles, allowing the sound to travel and for you to hear it clearly. This is the ultrasound. Now let's say that today we need something that performs the same function as the tuning fork, specifically for the probe. How do I do this? Pay attention to the fact that you need something that moves, something that changes in motion. This means you need something that has a rapid change in its movement. This rapid change in movement will start to create, and this is where the idea comes in. So we decided to use our probe. If we open this probe, it will function like a tuning fork, as it will emit the ultrasound waves necessary to create compression and rarefaction to transfer its mechanical energy. Now, let's see how the idea works. If we open the cover of the probe, we will find that there are elements inside, which I call crystals. There is something called piezoelectric material. What does piezoelectric material mean? It means that right now, I want to do something. I want to take a specific material and apply mechanical effects to it, or change its motion, or alter its dimensions very rapidly. This change results in ultrasound. Here is the probe, for example, in this shape. So I have the probe in relation to me. Here there is a part called the probe surface. The probe surface consists of elements or crystals. We took a material from them and said we would bring a material with piezoelectric properties. What are these piezoelectric properties? The material starts to do something called heating. And this heating continues until it reaches a certain temperature called the cure. At this high temperature, the material or crystal loses its dipoles. What does dipoles mean? If I look inside this material, I find that it contains molecules. These molecules consist of positive and negative charges. Each molecule or atom or particle has a negative charge and a positive charge. Now, what do I want to do? I want to create a certain structure for my crystal, which I will use later to control the crystal technology. Why do I want to control the crystal technology? I want to manipulate the crystal technology for me. And this is the orientation of the molecules that form the crystal for us. In the crystal, there is something called dipoles. Each dipole has a part with a negative charge and a part with a positive charge, like one end having a positive charge and the other end having a negative charge. Now, if you raise the temperature above a certain limit, known as the cure temperature for this crystal, it starts to lose its orientation inside, as if these molecules have begun to move freely. At this point, you start using an electric field, meaning you place this crystal between two electrodes, one of which is negative and the other is positive, to begin using orientation. For the dipoles, according to the charge, or the electrode you placed for the negative charge, which is the positive dipole, it will move towards the negative electrode and the negative will move towards the positive electrode. All right, so you did this orientation. In this case, what do? I take this device, or I bring the crystal with a certain structure that I created, or with the structure I made that has a specific orientation for the dipoles. I start to expose it to the electric field. As you can see here, this is negative and this is positive. So the molecules present will start to have a specific orientation, standing straight like this. Here is the negative electrode and here is the positive electrode. The molecules or dipoles have this orientation. Now, if I call this on, I am exposing the electric field. I will start to hold this pulse or the electric field application I made on the electrode. What will happen? The molecules or dipoles will start to relax. Once you remove the effect of the electric field, they will begin to return to their original structure, which I initially applied to them. All right? So what happened? If you pay attention here, you will find this thickness. The thickness, which is the distance between the positive and negative electrode, was such that when the electric field was applied, all the molecules were oriented in a parallel manner. So the thickness of the crystal seemed to be reduced in size. When I stopped the electric field, what happened was that the dipoles relaxed, leading to an increase in this thickness. The increase that occurred in the thickness means that I can apply the electric field again, but this time I reverse it, making the negative charge positive and the positive charge negative. It's as if you are reorienting the molecules or dipoles again. I will repeat this process quickly. You are reducing the thickness and then increasing it, reducing the thickness and then increasing it. This reduction and increase in thickness means you are changing the thickness of the crystal itself. The movement you are working on generates mechanical motion or mechanical energy, which causes the generation of ultrasound waves. This is the form of the ultrasound wave. The pulse, which is the electric pulse you apply to the crystal to achieve orientation or control the orientation of the dipoles present, will start to generate your ultrasound pulse. Your ultrasound pulse will provide, for example, a certain voltage or current applied to the electrodes inside the crystal, resulting in an ultrasound pulse. This is what happens, or the concept of the crystal. Of course, I don't have just one crystal. I can have up to over 500 crystals or 500 elements inside the probe. But right now, we are talking about a single element or a single crystal. Here is the shape of the crystal. Now let me show you something. Here is what happens. Here are the negative charges, here are the positive charges, and here are the dipoles. This is exactly what happens, as if you are doing